Hello everyone. I'm going to tell you about Mylar, which is a platform for building web applications on top of encrypted data. Many web applications today store confidential data at web servers. And we hear many times in the news that the data leaks from the servers. It is challenging to prevent data leakage because some attackers can get full access to the servers. For example, hackers notoriously break into systems by exploiting software bugs and sometimes even get root access to the servers. Second, more and more companies are hosting their web applications in the cloud, and hence some cloud employees can get full access to the servers and read customer data. And finally, the government also has been getting full access to the servers in certain situations. To prevent data leakage against such powerful attackers, we developed Mylar, a platform for building web applications that protects confidentiality against fully compromised servers. The approach in Mylar is to have servers store encrypted data, and plain text data only exists in the user's browsers. Each user has a key, and when the user provides some plain text data as part of the web application, the data gets encrypted in the browser before it gets sent to the server, and the server stores it encrypted. Later, when the user fetches the data gets decrypted in the user's browser. Okay? So you can see why this approach makes sense, because an attacker at the server only gets to see encrypted data. Server-side encryption has already been proposed in the file systems community, encrypted database community, and there have even been some basic proposals for browser encryption. However, these are far from sufficient for building real web applications. And here is why. First, they're not secure against active adversaries. Such an adversary could tamper with the web page and cause that the web page code leaks user data and user keys to an adversary. Also, they do not provide basic functionality, such as data sharing and computing on shared data. Mylar enables this through a set and addresses these challenges through a set of new techniques: web page code verification, principal graph and certification, using a client-side web framework to facilitate encryption, and developing a new encryption scheme, which we call multi-key search. So to explain how these work and how Mylar works overall, let me take as a running example a chat application. So in this application, Alice and Bob share a chat room called Work, and Bob and Eve share a chat room called Party. To enable this chat application securely, we need to provide a few features. First, the server should not be able to see the messages. Second, the users should be able to share chat rooms securely. What I mean by that is that a user should be able to see the messages in a chat room that he created or that he was invited to, but should not be able to see the messages in another chat room. In terms of computation, the application should be able to format messages and generate an HTML page, and users should be able to search over the chat messages. Okay, so to enable this, the very first question is, how do we even organize a web application framework to facilitate encryption? And you might think about starting with the common web frameworks today, such as Django or Ruby on Rails. And in fact, that's what we did, but we then realized that they're not compatible with encryption. So let me tell you why. In these frameworks, the web server generates the web page from data in the database, current user information, and code. So let's try to add encryption to this kind of framework. Now, the web server is supposed to somehow generate the web page from encrypted data, and the browser should be able to decrypt the data. There are a few problems. First of all, the server's computation is severely restricted by encryption because we only know how to do a small number of operations efficiently over encrypted data. Second, since the web page is generated at the web server, an attacker at the server can easily tamper with it. For example, the attacker can insert malicious JavaScript in the web page, which takes the user data and user keys and sends it to evil.com. Okay. So the first thing we realized is that actually a client-side web framework, such as Ajax-style programming or Meteor, is much more compatible with encryption. Here are the features of such a framework. First of all, the data and the code are separate, and the code is static. It doesn't change. Second, the web page is generated on the client, not on the server, which means that this platform enables computation to happen in a user's browser. Okay, so with this new layout, we can easily add the first two steps in Mylar. The first is Mylar certifies the code that comes from the web server to ensure that the web server, the attacker, did not tamper with it. The paper describes how we actually do this certification, but you can see why it's easier if the code is static. Okay? So we trust the developer, we trust the client-side code of the original application, but the attacker, the server, could have inserted some malicious code, and that's what we want to prevent. Second, Mylar adds an interception point where it intercepts the data that leaves the browser and encrypts it, and intercepts the data that comes into the browser and decrypts it. Okay, so with these first two steps, we already handled a few things. The server cannot see the messages because we have encryption. Also, since the client-side framework enables computation in the user's browser, then we can format messages there and we can generate the HTML page there. Okay, so next, let's handle sharing. So remember that in the chat application, we want the user to be able to see the messages in the chat rooms that he created or that he was invited to, but no other message. Mylar enables the developer to specify access control through something called a principal graph. This is a graph of principals, which are units of access control. So Alice, Bob, Eve, chat party. An edge indicates access. So for example, Bob and Eve have access to the chat party. Assume that Alice wants to create a new chat work and share it with Bob. Then, in Alice's browser, when she clicks the Create Chat button, in Alice's browser, the principal create function runs, which creates a principal for work. And she automatically gets access to this principal. Then when Alice wants to invite Bob, the chat work, she clicks the Invite User button, which calls the Add Access function in her browser, and hence Bob gets access to this principal. Now, as part of the application code, the developer specified that the messages field of the messages table should be encrypted. And it should be encrypted in a way that the principal stored in the chat print column should be able to decrypt. So now when Alice sends a message as part of the chat work, the message gets encrypted and stored encrypted in the database at the server, and it's going to be encrypted in a way that the work principal has access to it. Okay, so we saw how the developer specifies the principal graph. Now, the way Mylar enforces it is with keychains. Each user has, and each principal has a key. Now, the key of the users is generated in the browser of the user when a user creates an account. The key of the chats also gets generated in the browser of the user who creates that chat. In fact, the server stores the keys that don't belong to users, so the keys of every principal that is not a user, but the server stores these keys encrypted, so it doesn't actually see them. Now, the key of the chat work is encrypted with the key of Alice and separately the key of Bob, so that these users can get access to the key. And naturally, the contents of each chat are encrypted with the key of that chat. Okay, so now when Bob wants to read the contents of chat work, he tells the server to give him the key for chat work, and he can decrypt that key and hence get access to the data of the chat. Note that Eve does not get access to the messages in the chat work because Eve does not have the green key encrypted under Eve's key. So she cannot see the contents of the messages in the chat work. But a malicious server attacker colluding with Eve could give access to Eve to the chat work. And here is why. When Bob wants to encrypt a new sensitive message for the chat work, he asks the server for the key of chat work. But the server is going to give him the key for the chat party. So Bob is going to encrypt this sensitive message with the key for the chat party, which Eve has access to. So Eve can decrypt that data. To prevent cheating during key distribution, Mylar uses something called a certification graph. This graph has similar nodes to the principal graph, but the edges mean something else. So an edge here means that a principal vouches for another principal. So for example, Alice vouches that the green key corresponds to the chat work by producing a signature on the binding of the two. So now Bob's browser can check when he gets the key of the chat work that there's a signature from Alice on the green key and the name chat work. And he can verify this, and Bob's browser can verify this with Alice's public key. But how does Bob's browser know that it needs to check a signature from Alice, and how does it know Alice's public key? For the second question, we use a trusted identity provider service, or shortly IDP. So this is used to bind a username to a public key, and is only invoked once when a user creates an account. And in fact, we show in our paper that a large class of applications don't actually need an IDP because they have something called static principles in their application logic. Okay, but how does Bob's browser know that he needs to check a signature from Alice? And that is done with help from the user. Principals have human meaningful names, as we've seen so far: work, Alice, Eve, Bob. The developer is supposed to display to the user the entire certification path that uniquely identifies a principal. And then the user must choose the path. So for example, work by Alice indicates the principal work that Alice and Bob share. And now even if Eve is malicious and colludes with the server and creates another work chat room, the user can see that the second work chat room was created by Eve and not actually introduce messages in that chat room. Okay, and this kind of choosing a path is the only change to user experience in Mylar. So everything else in the interaction of a user with the web page remains the same in Mylar as in a regular web application. All right, so we need to handle search now. So we'd like the search to happen at the server because it would be very inefficient to download a large amount of data in a user's browser and search locally. But the challenge is that a user's data is actually encrypted with different keys, as you can see in the case of Bob. There are searchable encryption schemes that enable you to search over encrypted data, but they only work with a single key. Namely, if Bob's data was only encrypted with one key, then he could encrypt the word he searches for, let's say place, with the same key, and the server would be able to identify the match using the existing search schemes. But Bob's data is encrypted with different keys, so Bob would have to repeat this process for every key that his data is encrypted under. And this can be very slow when Bob has a bunch of different keys, because for every key, Bob has to fetch the key by finding it in the principal graph and certifying it using the certification graph, and that can be slow. Instead, it would be much more efficient if Bob could encrypt the word place under his own key, and the server somehow be able to do the search using that encryption. For that, we provide a new encryption scheme, which we call multi-key search. The idea here is that the server adjusts the encryption of the data from one key to another key. And this crypto system is based on elliptic curve mathematics. I won't tell you how it works, but here's the API. And let me tell you about the more unique parts of the API. Delta and adjust. Deltas get generated in a user's browser. For each of the chats that Bob is involved in, he generates a delta from his key to the key of the chat and gives the delta to the server. So he has a delta from the black key to the green key and a delta from the black key to the purple key. Okay, so now the server has these deltas. When Bob wants to search for the word place, he just encrypts it with his key and gives this encryption to the server. Now, the cool part is that using the deltas in the adjust function, the server can adjust the encryption of the word. So from the black key to the green key, and from the black key to the purple key. And from that point on, the server can just use the existing single key search schemes as before. Okay? So the point is that the delta and the adjust enable us to map a multi-key situation to a single key situation and use existing schemes. Okay, so that's how search works. And we have now enabled the chat application securely. In general, Mylar provides the following confidentiality guarantees. It protects user A's data confidentiality against full server compromise and compromise of any user machine except for users with legitimate access to user A's data. And it assumes that the developer's client-side code does not leak data. And one can use existing schemes to ensure that the developer doesn't make stupid mistakes. Okay, Mylar does not protect against side channels or access patterns and does not hide metadata. Its goal is to hide data content. So we implemented Mylar on top of Meteor, but its design is not limited to Meteor. It takes 9,000 lines of code, JavaScript and C++. And we evaluated Mylar in a variety of ways, and let me tell you about two of them. Developer effort to port applications to Mylar, and performance overhead. Regarding developer effort, we secured 6 applications with Mylar, 3 of which already existed. The chat application, a medical application. This is a medical application of Newton Wellesley Hospitals in Boston, which collects patient data regarding the endometriosis disease, and is currently secured with Mylar and tested by patients who suffered from the disease. We also secured the class submit website, a photo sharing application, a forum, and a calendar application. The cool thing to notice is that the average lines of code we added to port these to Mylar was only around 36 lines of code, which is small. So how about performance? The experimental setup consists of a powerful client for throughput experiments and a network that approximates a nearby data center. For kChat, oops, something weird happened. The image cannot be displayed. Your computer may not have enough memory to, okay. Anyways, so, yes, this is all performance. So, okay, so the latency overhead for the most common operation transmit in kChat was 50 milliseconds. And for the other operations also it was less than a few hundreds of milliseconds. And the throughput reduction in number of messages per second was 17%. So this is compared to kChat without Mylar and Mylar. So we basically conclude that for a large class of applications, Mylar provides modest overhead. So in conclusion, Mylar is a web application platform that protects confidentiality against full server compromise. It secures real applications with few lines of code and has a modest overhead. And this is through a set of new techniques web page code verification, principal graph and certification, and a new encryption scheme. So Mylar is open source, so secure your web application with Mylar, and come to our demo. Thank you.
Nice presentation. So you mentioned one of the chat applications where, say, Alice and Bob are sharing a chat window, and Bob and Eve are sharing another chat window. And you said that if Bob wants to write something to the chat window that he shares with Alice, but not with Eve, the way you work with it is to have Alice sign the chat and the principal graph, right?
Yes.
And Bob has access to Alice's signature, and so he can actually write to that, and it does not go to Eve's. Now consider the situation where Alice and Bob are sharing a chat window, and Alice, Bob, and Eve are also sharing another chat window. Alice is the principal. The signature would be the same, right? Because it's created by the same user. Mm-hmm. How does it work then? Because, I mean, do you get the question?
Right. So, for example, in that case, what should happen is that whoever is the creator of the room, let's say Bob, should choose a chat room that has different name. So then they have different names and different meanings to the user. Now, if that user who creates the rooms, Bob, the common user, is malicious, then, well, he anyways have access to the data.
No, I'm talking from the server-side attack where, say, Bob is requesting for the signature or the data to be posted to the certain chat window, and there is a server-side attack, and the attacker instead provides the signature for the other chat window, and that was the problem, right? So let's say there is the same problem here.
So the point is that what the signature path attests to the current user is that the certain user is trusted, so the creator of the chat room is trusted to have created a certain chat with a certain name. Now, if that user who's trusted creates two different rooms with the same name, then, the user assumes he trusts that user. So it's really not, it's a different kind of, it's not in the threat model.
Okay, so it's based on the name as well as the signature then?
Yes.
Thanks.
Hi. My question's about incentives. Service providers use data as an asset. Today they might want to do search. Tomorrow they might want to do face recognition on all your photos. And day after they might want to do ads and so on. And we have had a bunch of these systems in the past that do privacy-preserving X, right? But it doesn't do privacy-preserving Y, and so for Y you need yet another kind of encryption and third kind of encryption. Very quickly it ends up being homomorphic encryption that's not going to be practical anytime soon. What are your thoughts on how to incentivize service providers to actually provide privacy to users without having to subsume the risk of not being able to access their data for arbitrary purposes in the future?
Right. So basically, there are at least two types of clouds. In the first type, a customer is placing their data in the cloud in a pay-per-use model, so they pay the cloud to use the resources. In that situation, the cloud doesn't care to see the user's data and doesn't usually want to see the user's data because they can make profit from the pay-per-use model. So Mylar suffices in that case. Now, in the second case is Google and Facebook, which actually make money from seeing a user's data. And there, I think, yes, indeed, there are some proposed techniques for enabling recommender systems. I also don't think they're quite there. But all that this says is that this is an interesting future work question, and I would like to keep thinking about how to enable such recommendations and additions and add services over encrypted data.
Hi, Sophia Wang, University of Washington. Very nice talk. So I really want to know what is the trust base if I would like to use Mylar?
Yes. So you don't trust anything at the server. What you trust is with your data, you trust your browser and your machine. And you also trust the client-side code of the developer.
So that is also part of the web page, but it's not the server-side code.
Exactly. So you don't have to trust the server-side code. You just trust the client-side code. Also, So you trust the developer who wrote that code. But note that an attacker at the server could insert code in the client-side code, but Mylar's code certification prevents that from happening.
I see. Thank you.